All right, welcome everybody. So in this video, we are going to take a look at what an orthogonal complement to a subspace is and take a look at an example using matrix subspaces, the column and null space for a matrix. So let's first define what an orthogonal complement to a subspace is. So a vector z, if it is orthogonal to every vector in some subspace W of Rn, then we say that Z is orthogonal to that entire subspace W. And the set of all such vectors Z that are orthogonal to the subspace W, that is called the orthogonal complement of subspace W. And we denote this with a W and a superscript with the perpendicular symbol over here. So this W with this superscript is telling us orthogonal complement of W. It is the set of all vectors that are perpendicular to every vector in W. So let's take a look at an example with a picture. So let's imagine that we're working with R3. And we've got two vectors in R3. We'll say V and W. So maybe here is vector V, and here might be vector W, and this plane that I've labeled W, this would be the subspace spanned by those two vectors V and W. So then we would say that this vector Z is orthogonal to subspace W because this vector Z is the normal vector to this plane. Okay, so it is perpendicular to every single vector in this plane. And the orthogonal complement to W is going to have to be any vector which is some scalar multiple of Z. So here we can pick a positive scalar multiple and move off in this direction, but we could also go in the exact opposite direction and choose a negative scalar multiple, and that also is going to be perpendicular to all of the vectors in this plane. So therefore, we can write the orthogonal complement of W as C times vector Z. So in other words, any scalar multiple of this vector Z is going to be orthogonal to the entire plane of vectors in W. And below, I've got two important observations here. So the first observation says that a vector Z is going to be in the orthogonal complement of some subspace W if and only if Z is orthogonal to every vector in a set that spans W. So this set W, right, it has an infinite number of vectors, so it would be quite difficult to pick every single one of those vectors and show that Z is perpendicular to all of these vectors. But what we know about this plane W is that it's the span of two vectors. So that means any vector in this space W can be written as C1 times V plus C2 times W. And so if I take this vector and dot it with Z, as long as Z is perpendicular to each of these vectors V and W, then using the properties that we've shown for the inner product, namely we can pull out scalar multiples and we can distribute this inner product. So I can write this as C1 times V dotted with Z plus C2 times W dotted with Z. And so if I know that Z is perpendicular to V, then its dot product is 0. And if I know that Z is perpendicular to W, then this dot product is also 0. So what we can see is that if we take the dot product of Z with any vector in the span of V and W, that it's going to be orthogonal to all of the vectors in that subspace. So therefore, I don't need to check every single vector in the subspace W, but rather just make sure that these vectors Z that are orthogonal to W should be orthogonal to each vector in the spanning set of W. And the second comment is that W, the orthogonal complement of W, is a subspace itself of Rn. So recall in this case, the orthogonal complement is the set of all vectors on this line that goes through the origin. And if you recall from what we learned about R3, that lines through the origin, those are subspaces of R3. Those are one-dimensional subspaces of R3.